In this problem, we have to design a hash set, and this is a problem which has been commonly asked in Google interviews. So we will see the problem statement, we will also see hashing in general, what are collisions, how do we resolve those collisions, and then finally we will implement our hash set class in C++, Java and Python. So let's first see the problem statement. So we have to design a hash set class without using any built-in hash table, and we have to add 3 functions in that. We can have more private functions, but the client of this class should be able to use these 3 functions. So add value, insert a value into the hash set, and in hash set or set in general, we don't allow duplicate values. So these should be unique. This is different from hash map, where there is a value associated with keys also. Here we are just bothered about key. So this value you can think of as key, some integer. So here only values are present, not key value pair. So you should be able to add value into the hash set. You should be able to check whether a given value exists or not. So this should return bool. And then you should be able to remove a given value from the hash set. So this is the specification. So first let's see what is hashing. So the purpose of hashing is to distribute keys or entries across an array of buckets. So this is hashing in general. In this case, we are talking about just hash set and not hash map, but the underlying concept remains same. Only thing is that here we don't associate a value with a key. So here we will have just key or value, whatever you want to call it. So in essence, you have a hash set. You can think of it as a system. Or you can call it hash table, hash map, or in this case hash set. So you enter a value x. So what it internally does, it calculates, it has a hash function. And in general hashing, this x, this key may not be integral value, it can be even a string. So what this hash function will do, it will take this int and convert it to a number. Let's call it k. And there is another step. So you can call it 1, and you can call it another function f2 which takes k and maps it to 1 to l minus 1 or n minus 1, let's say. So n is the number of buckets. So a very simple function for f2 can be that take the modulo. So whatever is k, this can be a big integer out of this range. So this will take modulo of this. So k modulo n. So this value is now between 0 and n minus 1. So let's say we have a table, or you can think of it as an array or a vector of size n. So last index will be n minus 1, first index will be 0. So first it converts this input to an integer. In our case, we will not need this one. We will use just this one since we already have an integer. And the second thing is that it converts it into a given range. The range is from 0 to n minus 1. So now you can, whatever is the value output of this f2, you can directly go to that index, since that will be a valid index in this table. So you go there, but there is a possibility that multiple inputs will map to the same output. So in general, if you have more number of inputs coming than the size of this, then definitely there will be some collisions. Collision is a term which we use when multiple inputs map to the same index. So now this key will be stored at this. So if there is no other value, then we put x here, or let's call it x1. Next, we want to insert x2. x2 is inserted, let's say here, map to this index. Then x3 comes. And let's say x3 maps to this x1 again. So what we will do, we will append it in the end. So this is how we will address this collision problem. So we will come back to it, but before that, let's see what is collision. As we have already used this term, collision when so we input x, and let's say this combines everything, these 2 functions. And again, a reminder, in our case, we will just use f2 since we already have integer. So this will output an index, idx. So if multiple inputs map to the same index, then how we are going to store that. So this phenomenon is called collision, and there are different methods of resolving collisions. So one of the methods is called separate chaining, which we just saw, and we will use this one only in our solution. So separate chaining means x1 and x3 are mapped to this index. Let's say this index is 0, 1, mapped to 1, and this index is, let's say, 95. So we will chain them. There is a chain of these keys, and when a new key comes, we create a bigger chain. So this is called chaining, and when we are searching for it, we will use the same hash function. So it will again map. Let's say we are searching for x3. So it will pass through this hash function and generate index 1. So we will come here. If its size is empty, we are sure that x3 does not exist, because if x3 has to exist, it will exist at this index only. So if this is empty, there is no chain, then we return false. Otherwise, we compare with first value. It does not match, so we go to next value. So until we find it or we reach the end, we keep searching for it. So this is how search will work. Similarly, while removing, let's say we want to remove x3, first we need to search and then remove it from this. So its size will decrease by 1. So this way of addressing the collision is called separate chaining. There are other methods like open addressing. So the simplest method in open addressing is linear probing. So probe means explore. So we have to explore. Let's say in this case, we are not forming a chain like this, but we are storing every value in this array itself. So this has to be clearly larger than number of inputs. So let's say our hash function maps it to this location. So we put x1 here, and then we insert x2. Let's say x2 was inserted here. Then again we input x3. We want to add x3, and again it maps to this location. But this location is already occupied. So what we will do, we will check the immediate next position, one index next. So if it's again occupied, we will check the next one. So we will keep doing this until we find a blank spot, and then we will put here. Let's say some other value was here. So this is called linear probing. There is quadratic probing also. So even in searching, we will follow the same thing. We are searching for x3. It maps to here, but there is another value. So we don't return false, but instead we look at next spot. It's also occupied. Next spot, we found x3. And if we found a blank space, then we say that it does not exist. Similarly for removing. But while removing, let's say there were 3 values mapped to the same index using the hash function. So let's say we want to remove the middle one. So if we simply remove it, then while searching for x3, we come here, we don't find it, we go to next location, we found open position, we will return false. But that's not correct. x3 was actually here. We had just removed some value from between, so it was hollow. So when we remove, we assign some dummy value here, so that while searching, we don't stop here. We see that there was some value, so it was removed. So maybe x3 is next to it or further next. So this way of addressing is called linear probing, and it comes under open addressing. We have quadratic probing also, where it's not just one, but some different function. And then we have double hashing. So first hashing will map the input to this key, and if it's occupied, the job of second hash function will be to decide where to look next. So in this case, we were probing with an offset of 1. This in this case, double hashing, this second hash function will decide by how much to probe for the key next. So this is another method, but we will focus on this. You can study about these methods in detail. So we will focus on separate chaining here, and it will be very simple to implement. If you had already seen some of the lessons on graphs where we use adjacency list, so there we have something similar to this. We have a table with size equal to number of vertices, and all the neighbors are inserted one after other. So you can draw some similarity out of that. So if you have implemented that, it should be easier for you. So this is hashing in essence. Now let's see about a popular term that is used in context of hashing is load factor, which is a critical statistic for a hash table, and it's defined as n over k. So n is the number of entries occupied in the hash table, total number of entries, and k is the number of buckets. So let's say we have inserted 1000 keys and our bucket has 15,000 spaces. So load factor will be 1000 by 15,000. So it will be 1 over 15 or 0.0. So this is a small load factor. Let's make it 10,000. So it will be 2 by 3 or 0.667. So this is a reasonable load factor. We keep load factor below 1 generally, and in fact in Java 10, if the load factor is crosses 0.75, then we rehash. We rehash so that the length of chains decreases, and we try to generally keep it to a small number. So this is one of the metrics. Another metric is that in this case we are not looking at the chain sizes, that is on average how many keys are present, what is the variance. So another parameter is to look at variance. So let's say we have two hash tables, T1 and T2. Their load factors are same, that is their number of buckets is same, number of keys inserted is same, so their load factor will be same. But let's say in first case we have one of the buckets has 1000 keys and others are on average having less than 0.25 keys, and in other case all the buckets are having good amount of keys and not this kind of variance. So extreme case you can think that all the keys are mapped to same location. So in that case the time taken here will be linear and not O of 1. So clearly T1 will be not a good hash function. T1 is not using a good hash function. That's why here the variance is very high. All the load factor is same. So this is another parameter that is used to check whether we need to rehash or not. Now let's come back to our problem statement. We have to add, contains, and remove. So what we will do, we will define a bucket size. Let's call it bucket size equal to 15,000. And in the problem, it's given that we will have values in the range of 0 to million, and number of operations is 1 to 10,000. So maximum 10,000 operations can be performed in total. So maximum number of additions can be 10,000. So maximum number of 10,000 keys can be there in the hash set. So we think of 15,000 as a reasonable number. We can even take a smaller value. So in this case, load factor can go maximum up to 0.667. We can even take 10,000, and we will try with different values and we will see whether there is a difference in time or not. So we will define a bucket size, and we will define a vector of int called buckets. You can also take it as list, and in Java you can think of it as a list of lists in Python, and in Java you can think of it as a array of lists. So anyway it conveys the same thing. So we define something like this. So its indices are from 0 to 14999, and each of them is a vector in itself. These are all empty initially. So whenever we insert, what we will do, our input is already integer in the range 0 to 10 to the power 6. So we just take modulo this value, bucket size. So it will map to one of these, and we will check whether it exists in this or not. So this add operation will depend on the size of chain. So the idea of a good hash function is that it distributes the keys evenly. So if we have more number of buckets compared to total number of keys, that is called load factor. So if a good hash function distributes evenly, then on average we will have 0.75 keys in each of those buckets. So in that case, it should be ideally O of 1. But if we have a bad hash function where some of the chains are very long, then these operations are of the order of length of the chain, or we can call it C. So you get the idea. So if it's present already, we will not insert it. If it's not present, we will push in the end. So this is how we will define the add. Similarly, contains is very similar. In add, in fact, we used contains. And then while removing also, we first find it. If it's found, we remove it. If it's not found, we don't remove it. So let's write the code for this. Or num buckets. So the constructor is done. Now we will define our add function. So we will define a hashing function. So we can do here itself. We can take key modulo this num buckets, but let's define a private hashing function so that in future, if you change the specification, you want to change the hash function, you can do it in this function, and we will not need to change any of these functions. So let's call it int hashing, or you can call it hash function, or find hash. Return key modulo num buckets. So this I will be in the range 0 to 14999. If find, so we go to buckets I, and this is a vector. So buckets I dot begin. So we will search from beginning till end. And we want to look for key. So if this is equal to buckets I dot end, that is the key was not found, then we insert it. And we are done with the add. Next we want to remove, so it should be very similar. So we find the hash function, then we look if it's equal to, if it's not equal to end, then we remove it. And here we will need to know the iterator where the key was found. So better store it in an iterator. So what we will check, if it not equal to then the key is present, so we erase it. And we are done. So if it's equal to buckets I dot end, then the key does not exist, so we don't need to remove anything. And then this thing is also very simple, contains. So if it's end, then the key was not found, so we return false, else we return true. So you can first define contents and then use in the add also. So if contains key, then return. If does not contain, then insert. But anyway, you will need to find this I, so I think this is okay. Now let's try. And this matches, so let's submit. And the solution is accepted. Now what we will do, we can also use list here. You can play with it, try with list. So make everything list. And this should work as it is. So try with these and see which one is faster. You can also play with the number of buckets. Now we will write the same thing in Java. So let's copy it. Let's paste in the end so that we can refer it. And here we will use a list array of lists. So we can keep it as 15,000 and new linked list num buckets, and this will remain same. So here we have not initialized the buckets. So we have created a array of data type list of integers, but whenever we are first inserting to that index, we need to instantiate that. So that will not be initialized beforehand. So first time we go to an index, it will be null, the value. So we will create a new list. So if buckets I is equal to null, then buckets I equal to new linked list of integers. So it's initialized now, and so instead of find we will have buckets I dot index of. So in linked list we can search for a given key. So if it's not there, the index of will return -1, otherwise it will return the index. So if index of key not equal to -1, so it's already present here, so we will not need to insert it. So if it's -1, that means it's not present, so we will insert it. So buckets I dot add key, and that's it. Similarly in remove, if it's null, then return it's not present, this bucket is empty, this has not been initialized, no key has been inserted to this index, so return. If it's not null, then what will happen? If index not equal to -1, then buckets I dot remove. So we can store it in a dummy variable, and we are done. Next, contains. So if buckets I is null, or buckets I dot index of key is equal to -1, in both cases we have to return false, else return true. And now let's try. Let's delete this. And run it. And this works. So let's submit. And the solution is accepted. And the time is 11 milliseconds, and we are right here. So looks like there are not big chains, but let's reduce it to a small number. Let's say we have just 150 buckets. And now let's submit this. Now we can assume that there would be long chains. So you see time is 20 milliseconds. You can try with different values, and here you should at least see some trend that if we decrease the number of buckets dramatically, then we should have longer chains, and on average the time should be more. Now we will write the same thing in Python. So we create empty list for all 15,000 buckets, and then in add, so we need to define our function, hash function. If not key in self dot buckets I, if it's not there, then we insert it. If it's present, we don't need to do anything. Similarly in removing, if it's present, then we remove it, otherwise we don't. If key is present here, return true, else return false. And again it matches, so let's submit. And the Python solution is also accepted.